Hi everyone, we are Kruti and Riya. Today, we'll be talking about where lane detection models fail and why those failures matter. Lane detection isn't just vision. It decides if a vehicle stays in its lane. As autonomy scales, reliability here becomes critical for safety. It directly impacts whether a vehicle stays in its lane. Now, models like CLRNet report an F1 score of 0.796, which seems strong. But this is an average, and averages often hide critical failures. So we asked, where does the model actually fail, and what do those failures look like? Most prior work focuses on improving performance. Models like CLRNet, SCNN, and LaneNet push benchmark scores higher, but they don't analyze failures in depth. Explainability methods like Grad-CAM exist, but they are rarely used to study failure behavior. And robustness work applies augmentation broadly, without identifying which scenarios actually needed. So there is a gap. We improve models, but we don't fully understand their failures.
Our approach is much more diagnostic and not just architectural. We are not trying to build a new lane detector. We are trying to understand where a strong model like CLRNet breaks and why. So first we evaluate CLRNet across all 9 CULane scenarios to build a detailed failure map. Then we use Grad-CAM to compare where the model focuses in success cases versus failure cases. After that, we then stress test the model with test time augmentation. That means we modify the input images and inference time using pre-processing methods like CULane, gamma correction, and sharpening without retraining the model itself. Finally, we build those hard cases back into the training through augmentation-aware fine-tuning. This gives us a full pipeline, identifying the failures, inspecting the attention of the model, testing whether pre-processing helps, and then seeing whether training on those difficult cases actually improves the robustness of these models. From this, we get 3 main insights. First, aggregate metrics hide what is actually happening. Augmentation recovered lanes in many failure cases, but the overall F1 barely changed. This is because some images are so degraded that the lane detection itself is difficult, even under human inspection. Those structurally irrecoverable cases suppress the aggregate score and hide the real per-image improvements. Second, test time augmentation hurts more than it helps. Since the model was never really trained on these transformed inputs, augmentation creates a distribution drift and performance drops across all scenarios. Third, data fixes help, but only up to a point. Fine-tuning recovers some performance, but the gains are small and the hardest failures remain. So overall, we see 2 different types of failures. One is a perceptual failure where the lane is there, but it's really hard for the model to see. And the second is structural failures where the problem is deeper and tied into the scene geometry of the image itself.
Before making any changes, this is our baseline. In normal scenarios, the model performs very well. The predictions are accurate, the lanes are clean, and everything looks correct. But when we look at Grad-CAM, we notice something subtle. The attention isn't perfectly focused on the lanes, it is slightly spread out, sometimes even pointing towards irrelevant regions like trees. So even in ideal conditions, the model's understanding is not entirely precise. Now, moving to highlight scenarios. Here, the model is still able to predict lanes, but because of glare and bright reflections, the attention starts drifting. Instead of focusing cleanly on lane boundaries, it gets distracted by bright regions. So the prediction is correct, but the confidence and focus are already weakening. In night scenarios, this becomes extremely noticeable. The lighting conditions are poor and the model only predicts one lane, missing the other entirely. The attention is weak and scattered, showing that the model is struggling to extract meaningful features. And then we have curves. Here, the model often predicts the lanes correctly, but the attention is not aligned with the actual lane structure. It's more diffuse, less precise, indicating that the model is not truly capturing the geometry.
Now we can see where the model is actually starting to break. In the night scenarios, the failure is especially severe. The lane markings are so faint that the model does not have a reliable signal to work with. Its attention shifts towards headlights and nearby vehicles instead of the lane itself. And in some of these images, the lane is not just hard for the model to detect. Even for a human in the loop, they would struggle to confidently identify it. So this is not a simple model error. Some cases are visual evidence that it is extremely weak. In highlight scenes, glare becomes the most dominant signal, so attention shifts towards brighter regions of the road rather than the actual road markings. In curve scenarios, there is no single distracting object. The model is looking at the road, but its attention is too spread out to follow the lane geometry correctly. So these failures are not just random. In some cases, the model looks at the wrong thing. In others, it looks at the scene, but it's still difficult to interpret the structural geometry of the image. Next, let's look at where we intervene. We come in by changing the input, not just the model. For the night images, we used CULane to boost the local contrast and make the faint lane markings more visible. For highlight images, we reduce the dominance of the glare and sharpened edges, so the lane becomes much more easy for the model to separate from the brighter background. For curves, we enhance the contrast to make the road structure clearer. In several cases, this actually works. In the night scenes, weak lane markings become much more visible and the model's attention becomes much more focused towards the lane. In highlight scenarios, our glare is reduced, so the lane becomes a much more stronger signal as compared to the background. For curves, the lane becomes much more clearer after pre-processing, but the attention pattern changes very little. This is important because this suggests that pre-processing did not really change what the model was looking at, but it just made the signal stronger enough for the prediction to flip. But pre-processing also has its clear limits. In the night images, even enhancement after augmentation, there is no clear visible lanes. At this point, the issue is not just the model failure, but the visual signal itself for these images are missing. In highlight cases, pre-processing can sometimes overcorrect. When glare reduction is too aggressive, important cues get distorted and the model becomes even more confused. And in the curve scenarios, we see a slight shift in attention towards the correct path, but the model is still failing to detect the geometry of the lane itself. So this is the boundary of what pre-processing can do. Some failures are recoverable, but are fundamentally harder and need much more input enhancement. They require better modeling structure, geometry, or human oversight in extreme cases. Thank you.